9.1, rational and reciprocal functions. So if you are watching this and the year is 2021 and it's sort of mid-March, beginning of March, really it is an important lesson, the rational functions that we took in class. We're going to build on that knowledge of rational functions, and really this should be a straightforward lesson. So for example, recall the definitions from rational functions. A horizontal asymptote on a function as x goes towards infinity or x goes towards negative infinity, the value of the function approaches some constant c. Now remember that horizontal asymptotes are left-hand side and right-hand side behavior. So the function will go towards some constant as x gets large on the left and right side. Now a vertical asymptote, oh, and by the way, how do we find the horizontal asymptote? Well, that is when you compare the degree of the numerator with the degree of the denominator, and you end up with a horizontal line of y is equal to 0. Y is going to be equal to the ratio of the leading coefficients of the numerator and denominator respectively, or simply if the degree of the numerator is greater than the degree of the denominator, we don't have any vertical or horizontal asymptotes. Now let's look at vertical asymptotes. Vertical asymptote on a function, as x approaches some constant c, the function f of x will either go towards positive infinity or negative infinity. All right, so I'm going to sort of talk about rational and reciprocal functions as transformations, and I'm going to actually talk about using rational functions knowledge. So the reciprocal function 1 over f of x can be obtained. So if we have some function f of x with points x, y, the reciprocal function 1 over f of x will have points x, comma, 1 over y. So simply put it into words that when we take the reciprocal of a function, we could treat it as a transformation in which we simply take the reciprocal of the y value. So I'm going to take x values here. So if x is equal to 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. If I have the function, now I'm going to graph y is equal to x. If I have the function y is equal to x, well then the y values will simply be the same as the x values. So allow me to graph those, and we saw this very similar, that this is called the identity line. There. So let me graph the reciprocal function. So if we start off with y is equal to x, the reciprocal function, I can graph y is equal to 1 over x. And the reciprocal function simply will be, I'm just going to take my points, I'm going to take the reciprocals. Now, I am going to talk about this point. If I take my function and I have point 0, 0, and I'm going to graph the reciprocal function. So 0, 0 maps into 1 or 0, comma, 1 over 0, right? What's weird is that this is undefined. But thankfully, we did rational functions. And we know that whenever the denominator or a factor of the denominator is equal to 0, we will have a vertical asymptote. And that's going to be kind of important. So I'm just going to start graphing this. So wherever f of x has a 0, the reciprocal function, wherever my x-intercepts, the reciprocal of my function will indeed have a vertical asymptote. Now here's a point Now, here's a point here that I would like to talk about, and that point is going to be, that point is 1/2, 1/2. Now, why am I doing this? Because if I do point 1/2, comma 1/2, and if I take the reciprocal function, I have to take the reciprocal of the y value, which is 1/2, and that turns it into 2. So that goes way up there on the reciprocal function. 1, 1 is going to stay as 1, 1. 1, comma 2 will change into 1, comma 1/2. Sorry, I made a mistake there. Let me just delete that. 2, comma 2, when I graph the reciprocal function, it'll turn into 2, comma 1/2. And I can do this for 3, etc., etc. But also, what we know is this graph, my green graph here, I'm just going to sketch it out. What do we see? The green graph actually has a horizontal asymptote at y is equal to 0. Simply because as x gets infinitely large, it appears like this function, the function y is equal to 1 over x, will have a horizontal asymptote at y is equal to 0. So we can do it through transformations. However, if we think about rational functions, obviously this will have a horizontal asymptote at y is equal to 0, because the degree of the numerator is less than the degree of the denominator. Also, I know that this has a vertical asymptote, where my bottom, my denominator, is equal to 0. And this happens where x is equal to 0, and that's why I had a vertical asymptote there. So I'm doing it in transformations, but really I don't need to do them in transformations. So I'm just going to fill this in undefined 1, 1/2, 1/3. Now, you can transform it on the graph, or you can just simply take your x values and plug them into y is equal to 1 over x, and what you get, where x is equal to 4, the y value would be 1/4. So you had point -3, -3. It goes into -3, -3rd. You had point -2, 2. When you transform it, it actually turns into 2, comma, -1/2, -1, -1, stays where it is, etc., etc. And you end up with this very nice shape. And in fact, there it is. There it is. Here's our function. I hope this helps out here. So I'm going to delete some of this information. Actually, a lot of it over here. And I would just maybe like to delete it. Done. And I'm going to make 2 columns. And I'm just going to say f of x. And I'm going to look at this from a transformation point of view, and it's a reciprocal function. If f of x has an x-intercept, on the reciprocal function, that f of x is now in the denominator. Any x-intercepts or 0 turn into vertical asymptotes. If I have some point x, comma 1 on my function, well, when you take the reciprocal value of the y, well, the reciprocal of 1 is 1. So this is called a stationary point, if you recall. Similarly, x is x, comma -1. If x, comma -1 exists on f of x, when you take the reciprocal, it's going to remain the same. So these two are stationary points. And always, 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 f of x, when you're doing reciprocal functions, should I use the word always? How about I'll qualify this, and we're not talking about rational functions, we're talking about reciprocal functions. We have a horizontal asymptote at y is equal to 0. Simply because in grade 12, when I give you a function, when we take the reciprocal, the degree of the denominator will always be, the degree of the numerator will always be less than the degree of the denominator. So let's maybe look to graph this. We're going to graph y is equal to 1 over x squared by transforming the graph below. And the graph below is y is equal to x squared. So I know, you know, that you can graph this function using rational functions ideas. You could identify the horizontal asymptote, you can identify the vertical asymptote, and then you can plug in random values and you would get the correct graph. That would probably be the best way. However, I'm in 9.1, which is reciprocal functions. So what I notice is that y is equal to x squared. It has an x-intercept at 0. So that would imply y is equal to 1 over x squared. This is going to have a vertical asymptote at x is equal to 0. So in black, I have denoted my x-intercept. In red here is going to represent all of my reciprocal functions notation. So there it is. I have a vertical asymptote at x is equal to 0. Now, an interesting thing, if we use the notions of rational functions, we can also identify that the degree of the numerator is less than the degree of the denominator. So we get a horizontal asymptote at y is equal to 0. There we have it. And in fact, I feel so incredibly good about this. And I'm going to use the idea that if we have point x comma y on the reciprocal function, this turns into x comma 1 over y. We could use a table of values. I'm going to talk to you about which points I'm going to use. There, there, and maybe right there. Here, here, and here. For the most part, the points that I've chosen are those that are integers because it makes it real easy thinking. So for example, I'm looking at this point right here. This point here is -2, 4. So when I do the reciprocal of 2, -4, it gets moved into 2, comma, -1/4. So there's a point. And by the way, the left-hand side behavior, you know it's going to look like this because it's a horizontal asymptote. There's a stationary point, so I'm just, right, y is equal to 1. I'm just going to put dots wherever y is equal to 1, and I know that my function has to go through that point. Now, I'm going to take a look at this point right here. Now, I can make up a value, and I'm going to say x is 1/4. I don't even know. X is something, but y might be 1/4. So the reciprocal of 1/4 is 4. Now, as long as I get the x approximately right, nobody's going to complain or care too much. So there it is. On the left-hand side, that's what this graph looks like. Now, I'm going to do the same to the right-hand side of the vertical asymptote. So again, I'm just going to say my y value is 1/4, so that when I take the reciprocal of 1/4, the x value stays the same, but my y value is 4. And then I know that's a vertical asymptote but for sure, as I approach 0 from the positive side, that's what a vertical asymptote looks like. Now, I'm going to take this point here, 2, 4. 2, 4. So remember that all I'm doing is taking the reciprocal of the y value. It's going to turn into 2, comma, 1/4. Now, a lot of you guys just criticize me that that looks like 2 comma half, but it really doesn't matter too much. Behaviors of the graph are what really matter. So that's what my new function looks like. It's really nice to draw upon all of my graphing expertise from rational functions, though, for sure.